Hey everyone, welcome to Capturing Christianity. My name is Cameron Bertuzzi, and I am exposing you right there, watching, to the intellectual side of Christian belief. And tonight, I'm interviewing a cosmologist about the evidence for fine-tuning. We're going to talk about what that is, if you don't know what fine-tuning is. If you want to learn more about apologetics, see conversations between Christians and non-Christians, and discover arguments for God that you didn't know existed, make sure to subscribe to my channel and turn on the little bell notification so you can be alerted to new videos. Let me introduce my guest really quickly. His name is Luke Barnes. He's a theoretical astrophysicist, cosmologist, and postdoctoral researcher at Western Sydney University. He received his PhD in astronomy from the University of Cambridge in 2009. He has published papers in the fields of galaxy formation and the fine-tuning of the universe for life. He's the author with Geraint Lewis of A Fortunate Universe, and that's actually, we'll talk about this a little tonight. A Fortunate Universe, Life in a Finely Tuned Cosmos, published by Cambridge University Press. He has investigated the fine-tuning of the universe for intelligent life. He's modeled the effect of the cosmological constant on galaxy formation and the effect of alternative nuclear physics on stars. So he's legit. We're talking with the cosmologist about fine-tuning. So before we get into the interview, I want to introduce you guys to something we just started called the Bereans. The Bereans is a Patreon-only Facebook group by Capturing Christianity. So basically, if you sign up at the $5 tier or more on our Patreon, you get access to this private Facebook-only group. The name Bereans comes from Acts 17:11. The Bereans were a group of Jews that, quote, examined the scriptures every day to see if what Paul said was true. And so anyways, if you want to join that group and become a Berean, you can also get access to really cool gear. Like, I don't know if you can actually see this. It says, by the way, I'm one of the Bereans. Conversation starter. We also have these little mugs now. You can see, by the way, I'm one of the Bereans. So if you want to become one of the Bereans, then join the $5 tier on our Patreon, support us. And yeah, so let's move into the interview here. Let me pull up my interview screen so you can see who I'm talking to. I'm talking to Luke Barnes, Dr. Luke Barnes. He's like I said, he's a cosmologist, and he's an expert in this field of fine-tuning and cosmology and the conditions of the universe, how they had to be set just right for life to exist. So let's jump right into the interview, Luke.
Thanks for having me.
Yeah, no problem. We've had you on before, right? Because you had a discussion on fine-tuning with Alex Malpass, and that was it was actually one of my favorite discussions that I've heard. Not just because I hosted it, but it was one of my favorite discussions I've heard on fine tuning. Alex is great. You know, he's I don't know what you want to call him, but he's awesome. Look, take about 60 seconds and just tell everyone sort of what you do, the kind of work that you actually do. You write books, obviously, but and also explain why you're interested in this question of fine tuning in the universe and intelligent design, all that stuff.
I'm an astrophysicist and a cosmologist. So my main field of research is galaxy formation. So that was my sort of PhD topic, and it's a big field because galaxies are big things that come together in complicated ways. So that's sort of my main field of research. And in particular, I got interested while I was doing my PhD in this whole thing about fine tuning. And it sort of started off with, I was actually going to do a public talk, and I thought, I'll sign up for this topic, and then that'll make me read a whole bunch of stuff. And then it sort of got out of hand from there. One of the things that's great about it is that there's a whole bunch of wonderful physics about what happens if this parameter is like this or this law is like this. And if you're a theoretical physicist, that's all completely wonderful stuff. And so started reading a whole bunch of stuff, noticed that people were talking about fine-tuning who either didn't understand the physics or didn't understand the philosophy or both. And so started sort of critiquing a few things online and realized that actually there was this, very solid scientific literature that no one had really summarized at least for a good decades. And not only that, once I looked into that, I saw that there was openings in the field where you could go and look more into fine-tuning in more detail with better theoretical methods. So actually, one of the things I'm doing is looking at the way that galaxy formation and so star formation, planet formation, the way that depends on the way our universe has been set up using supercomputer simulations.
Well, let's first of all let's define what we mean by fine tuning. This is actually one of the first things that you do in your book with Geraint, and this is actually important to point out too, is that Geraint is not a Christian, he's not a theist, he's an agnostic, right? And so he wrote this book with you. He agrees that there's fine tuning. He just disagrees about what that implies. I think that's interesting. It's interesting to point out. But tell me about the definition of fine tuning. Your definition of it is actually my favorite. This is the one that I use whenever I'm explaining it, at least more on on a formal level, because I guess there's a couple ways that you could define it, but well, I'll let you do it since you're the expert.
Yeah, so I mean, the first thing to say is the fact that Geraint, who's agnostic or atheist, something like that, the fact that he agrees that the universe is fine-tuned means it doesn't mean that it's made by a designer. It doesn't mean that there's a fine-tuner. It might imply that, we can discuss that, but that's not the definition of the word. So when you're a physicist, you build a theoretical physicist, you build theoretical models to try to explain data, and you would like it to explain the data in a sort of natural way, in a way that makes you go, that's what's going on, and not in a completely ad hoc, jerry-rigged, sticky taped and super glued together kind of way. And one particular way that a model can look suspicious to us, if there's a free parameter in the model, so there's a number you've got to put in from the start. You don't get it out, you've got to put it in. And if that number has to have be in a very small range compared to what it could be, in order for your model to work, then we get a bit suspicious as to why, about the model in general, as to why this number should be in just this right range. So it seems like overall your model doesn't work unless you tinker with it in this special way. So all that fine-tuning really means is that there's some outcome that you're interested in. In that case, it was whether my model explains the data. And that outcome is very, very finely sensitive to the value of a free parameter, or the more generally the assumptions you had to put into your model in the first place. So then the fine-tuning for life is just that idea, which physicists use all the time. It's a bit of physics jargon. And you just apply it to one particular outcome, which is whether the universe could support life. And as a physicist, we really mean whether it could support the sort of complexity required by life. And it turns out that sort of applies. Seemingly small changes to the fundamental numbers in the best laws of nature we have very often render a universe in which we know what's going on because it's a really simple universe and nothing complicated ever happens. And in particular, it can't sustain the kind of complexity that any conceivable form of life would need.
So, so two things. So first thing is that I just want to reemphasize that by fine-tuning, we don't mean that it was designed by a fine-tuner. That is not what the term means. But I think in one of your papers that I was reading, I think it was actually a response to, correct me if I'm wrong, was it Victor Stenger? Was it the monkey objection or whatever?
Yeah, yes.
Was it him? Okay, so you had a paper on that, and in that paper, you defined fine-tuning in a way that it was just super clear. And so I want to give it real quick. This is off the top of my head, by the way. I didn't write it down. It's just from memory. But it was something like, of the set of possible physics, and this is what fine-tuning is, of the set of possible physics, the subset that permits the evolution of embodied conscious creatures is very small. So the subset compared to the set of all possible universes, the subset that permits the evolution of life is very small in comparison, basically. So I think that's a really easy way of understanding what fine-tuning means. Well, I mean, and it's hard to see how you could disagree with yourself, but maybe you do.
No, that's just about right. There's a couple of worries there that all possible physics, you really should be sort of changing the laws and equations as well if you're going to consider all possible physics. And we can do that to some extent, but not particularly systematically. We can change the constants systematically, which is why we usually focus on that as a tractable test case, a test case that we can actually, get our head around and do systematically.
So going back to your book. So by the way, if you guys want to pick up this book, it's in the description. It's also an affiliate link, so it helps me out a little bit if you want to do that. Just so go pick it up. It's about $10, $11, I think, on Amazon. Super cheap. Super great read too, because if this was actually some of stuff I wanted to talk to you about. Like, okay, so who came up with the names of the chapters? Was that you?
I think most of it was Geraint.
Really? So you both of you guys are just like, I don't know. There's a lot of humor built into this too. Like
Yeah,
chapter 5
we
is
have similarly stupid senses of humor. So
yeah. Well, anyways, so most of the book is actually
the one that's mine is chapter 7, and there's a sort of reference to, you know, something a bit more theistic there. So chapter 7 is a dozen or so reactions to fine tuning, which is a little reference to 24 or so arguments you may be aware of.
Yeah. So what was I gonna say? So most of the book is actually dedicated to like sort of explaining or looking at the evidence for fine tuning, which we're gonna do in this video. But I want to talk real quickly about the chapter 8, which is basically it's worth the whole book in my opinion, just to read this chapter because it's a great chapter. It's basically a conversation between you and Geraint about the implications of fine tuning. And so, why do you think that Geraint ultimately wasn't convinced in the end?
Yeah. So whenever Geraint gives a talk, so whenever we give talks on this and we say, what the last chapter of the book was in conversation, his audience asks him, "Why didn't you win?" And my audience asks me, "Why didn't you win?" Like, anyway. I think that one of the objections he raises there, I think it's the main one. I think the idea of a god just seems arbitrary. Like, I think if you're thinking in a sort of materialist mindset, that the way that reality is built is you start with simple stuff and you build from the bottom up. A mind is then something that a brain does, and a brain's a horrifically complicated thing. So the ultimate mind must be the most complicated thing there ever was. And so to start with that at the bottom of your worldview doesn't make any sense. It's because you put naturalism at the bottom to start with. But so I think it's
a very philosophical position.
Yeah, I mean, you do have to kind of turn your worldview completely upside down. It's not like just throwing in an extra thing into reality, just throwing a god in there somewhere.
Yeah.
So I think his problem would be like it doesn't try to explain a mystery with something that to his mind is even more complex and more mysterious is not progress. I think that's what he'd say.
Yeah, I feel like that's a pretty common view among people that it's almost like it kind of reminds me of the Dawkins type of, who created God type deal. Maybe it does, or maybe it's all sort of rooted in the same kind of concepts and ideas. Because there's a lot of people, even like not Sean Carroll, but Stephen Law thinks that objection, not phrased that way, but that type of objection where it's like if you can have God do it, then why can't we just have the universe do it? That's a really common objection that you hear from atheists.
Yeah.
All right. Well, so tonight what we're doing is we're discussing all of the evidence for fine-tuning. We're not going to really talk a whole lot about the implications of what this fine-tuning means. Rather, what we're going to look at are just the cases, like the actual scientific cases, and try to understand that and get your help to basically understand all the different cases. So how many are you aware of in total that there are? Like how many cases of fine-tuning are there?
So we need to sort of divide things up to start with. There's the ones where you try to change the laws of nature themselves, say change the form of the equations or something like that. Those are hard to count.
What do you mean by that? So like gravity itself, would that be a form of like a law of nature?
Yeah, I guess so. Well, we could start with there's an equation you can write down, which is the standard model of particle physics. And then there's sort of the standard model of cosmology, and it's very clear what the free parameters are in those equations because they're right there. You can just point at them. Right? Anything that's there's basically two types of things in there. There's something that represents something dynamical in the universe, like that bit of the equation there. That represents the field that makes electrons. All right, and that's a dynamical thing. It changes with space and time. And then there's a number in front of it. Or in front of that term, and that's the charge on the electron, which is about electromagnetism. So actually, that would be how electrons couple to. Never mind details. There's that number in there, and then there's the mass of the electron, and that number's over there, and then there's the Higgs mass, and that number's over there, and
these numbers are numbers that we discovered, right? We didn't just we're not plugging just random numbers in. We have to run experiments and get those numbers.
Yeah. So yeah, we you can't start with that equation and do some maths, and out comes the mass of the electron. What you have to do is you go and do a measurement of the mass of the electron, and we know that number to a lot of decimal places, like 10. I don't know. Someone look that up. Um, Once we've got that, we can take that number, we can stick it in the equation, and then it starts predicting a whole lot of other things about electrons and light and how they interact and all that sort of wonderful stuff. But when you've got the numbers in the equation itself, those are fundamental, meaning we have to go measure them. We can't get them out of the equation. The equation won't give them to us for free.
Okay, so let's get back to like the total number of cases, and you were giving like the different sort of categories.
So all I say is you could imagine changing the form of that equation.
What do you mean by the form of it? Sorry, I'm gonna have to break a lot of this down.
There's electrons out there in the world. There's a thing in the equation that represents electrons. Okay, and so we could imagine instead of that, we could try putting some other mathematical type of thing in there. So there's a question of whether it's actually, this is a bit too technical. Anyway, there's a particular mathematical object. You think of like the difference between like a number like temperature, which is just a single number, and velocity, which is speed in a particular direction. So I need one number for temperature. I need three numbers for velocity. I've got to tell you, direction and speed.
Time.
So whether it's a single number you put in, whether it's a list of numbers like a vector, or whether it's a grid of numbers, a tensor, whether it's a sort of quantum mechanical kind of thing, or all that sort of stuff. So we could imagine changing those sorts of things, and in doing that, you would change the identity of the electron to something else, or you would make gravity repulsive, or you would introduce a completely new force into the universe, or you might even totally overhaul the whole thing, forget space and time, and do all your physics on a grid. So we consider this in chapter 6 of the book. There's ways of simulating like universes on a two-dimensional grid, and you put in your own physics, and interesting stuff can sort of happen. It's hard to count those cases, but we can count the fundamental constants, and there's 31. And of those, I'd say they don't all sort of interact life as we know it, or the sort of complexity in the universe. So a lot of them are sort of weird properties of neutrinos, which are these particles that don't really interact much. So those ones aren't particularly fine-tuned. There's a central core of about, I'd say, 10 to 12, where you've got pretty solid fine-tuning cases where we've got the equations, we've studied these equations a lot because they describe our universe, we've got the number there, and we can start to think about what happens if I turn that dial. And so I'd say for 10 to 12 of them, we have a pretty good evidence. We know pretty much what happens if you start turning these dials. We know that something bad happens this way, something bad happens this way, and more generally, we turn multiple dials. We turn as many dials as we can at the same time. So we really start sort of, what if I turn this one and this one and this one and that one and these three together, and have all sorts of fun with that.
So what are some of the most popular examples of the 10 to 12?
So the most famous one is something called the cosmological constant, which has a long, interesting history. I'll jump to the end of it. The history starts with Einstein, but I'll jump to the end. In about 1998, we discovered that the expansion of the universe is accelerating. So we've known since the 1920s that if you look at a galaxy over there, it is moving away from us, and it's moving in a way that it doesn't matter where you are, the whole universe would look like it was moving away from you, so we're not at the center. But 1998, we know not only is it moving away from us, it's moving away faster today than it was yesterday. Now, we don't actually work that out by doing the measurement on 2 different days. That's too hard, but we have worked it out in other ways. The ordinary matter in the universe, sort of the stuff that, phones are made out of and all of this stuff, has an attractive pull, which would tend to slow the acceleration down. So there must be some other form of energy in the universe that's making it speed up. Okay, something's got to be causing this acceleration. Generally, a thing that's causing the acceleration of the universe is known generally as dark energy. And you call something dark energy when you don't know what it is, obviously. Um, or in particular, there's a particular type of dark
Just
energy
call it the Force.
the Force. Well, we don't want to we don't want to pretend anyway. There's a whole fan base there. We don't want anyway. For a particular type of dark energy, we call that the cosmological constant or an effective cosmological constant. That's the one. There's details there, but that's the one we think describes our universe. It basically acts like as if every little square foot of space had a certain amount of energy attached to it. And if you do that in the universe, it makes things expand. So, all right, that's the cosmologist saying, here's what we need. We need some of that stuff in the universe to explain what we see. And then
Okay.
particle physicist says, okay, here's an idea of what it could be. When we describe particles like electrons, they're not really particles. They're waves in a field, and they behave like particles. And suppose that so there's a particular way you make the field wave that represents one particle. So if you put a detector there, one particle would hit it. There's a way to make it wave where there's 37 particles. And there's a way to make it wave. There's a way to arrange the field so there's no particles. So you stuck a detector in there, it wouldn't go off. That's called the vacuum for obvious reasons, that there's no particles there. But the field is still there. And the crucial point is, if there's energy in the field, even when there aren't particles, that would act like a cosmological constant. That would make the expansion of the universe accelerate. And so, great excitement.
Even if there's no particles, yeah.
Even if there's no particles there. Great excitement. Hooray. Could this explain the expansion of the universe? And the problem is, when you do a rough back-of-the-envelope calculation in quantum field theory, the theory of these fields, you get it wrong by an enormous factor, 10 to the power of 120. And so the problem is there's in the theory there's a largest range that this number could have, and for various reasons you would expect it to be about of the order of that size, and that largest range is 10 to the power of 120 times larger than the actual value. And so now we start to think, okay, what could life put up with? And these are the simulations we've been doing. It's been known, pencil and paper, since probably the 70s or the 80s. Then we can now demonstrate this with supercomputer simulations that take a week to run on hundreds of computers, but produce really nice videos. That's important. If you cranked up this number by even sort of 3 or 4 or 5 orders of magnitude, you start to have the universe accelerate at a very early time before structure starts to form. And so by the time you're even 10 orders of magnitude, on your way up to 120 orders of magnitude, 10 powers of 10, up to 120 powers of 10, basically nothing in the universe sticks to anything else in the universe. And you don't have complexity, because what you very soon get is individual protons and electrons completely isolated in empty space, as the universe just expands so quickly that nothing sticks to anything else.
And you're not going to get life in that universe, not anything like we experience here, right?
Yeah. So I mean,
well, so let me back up real quick. So how did you get to the where did you conclude that there's all these different possibilities?
So within
of the numbers can be.
So you've got the equations, and I mean, there's a number in there, and you can just stick a number in there. One thing you can do is sort of, what would you expect for this number to be for, in particular, this vacuum energy form of the cosmological constant? The cutoff is the limits are basically there's a certain amount of energy. If you put so much energy into a small part of space and time, you come up against the limit. There's a very rough calculation you can do where you say, all right, how much energy would a particle need to have before it became its own black hole? And the reason why that's a significant thing to try to at least estimate is because we don't currently have, famously, physics does not have a theory which combines quantum mechanics with general relativity. So all the quantum stuff in the universe, like particles, and all the gravity stuff like black holes and space-time and all that sort of stuff, we don't have a theory which can put those two together. I mean, there's candidates, we can talk about that. That doesn't matter for us here, sitting in our rooms, because all the quantum things are really small and all the gravity things are really big. That's a very rough hand-wavy way of saying we're okay with these two theories at the moment. There's a limit. Once you get up to a certain sort of mass scale, or energy scale, E equals mc squared, it's the same thing, you would need a quantum theory of gravity to know what's going on there. And so the thought is, okay, something new happens up there, but let's at least use the theory we know in a domain we know it works, or at least is extrapolatable to, and ask if that, given that that piece is valid, how much cosmological constant would I expect? And if we just confine ourselves to the bits where it actually doesn't really much matter whether you go up to where we think our theory is valid or where we think it's at least extrapolatable to, you end up with this very large possible range versus a small life-permitting range.
So do you have anything else to add on the cosmological constant? I want to try to get to through a few of these examples.
It's just the best one because it's so clear for so many reasons. And in particular, it totally obliterates any sort of, oh, what about other forms of life? Well, if you think you can make a life form out of a single proton surrounded by a couple of trillion empty light years of, empty space, good luck to you. But the point is with fine tuning is that when we turn these dials, the universe makes a drastic step towards simplicity, right? Our universe is complicated. That's why it's able to do complicated things like life. It's these other universes which are really simple. I mean, if you're a theoretical physicist, they're great, right? You can just, you've totally got these ones nailed. You solve the equations and you've got them all worked out. But that's an example of why those sorts of, oh, what about other forms of life? Objections don't really have much sway. I mean, maybe for the marginal cases, they're interesting to think about, but there are these rock solid cases where, no, a single proton is not alive.
Yeah. Okay. Well, let's go to another example. What's another popular one?
So one that I particularly like, which is in the book towards the end, is we can look at the masses of the fundamental particles, and particularly the ones that make up us. So protons. So if you remember your picture of an atom, there's protons and neutrons in the middle, electrons going around the outside.
Mm-hmm.
Protons and neutrons themselves aren't fundamental. They're made out of small things called quarks. That's as far as we know. So that's basically we smash stuff together to try and find the smallest pieces. So far, the smallest pieces we know of are called quarks. All right. In particular, the up quark, they call the up quark and the down quark. Those names mean almost nothing because they're such simple things that, we don't know the personality of these little little things. So, all right, three particles, which make up all of the matter in the universe, except for dark matter, probably, but we can talk about that later. Dark matter can't
that's like
interact
dark energy, right? Something that we don't know about.
Yeah, we don't know what it is. It's probably a particle. It must have attractive gravity. We know that much. But it can't interact too strongly with itself because it's got to stay sort of diffuse and spread out to explain the way galaxies move. So it's not a candidate for the life in the dark sector. So that's not going to happen. Anyway, three particles. So three numbers, just the mass of the particles, mass of the up quark, mass of the down quark, mass of the electron. So there's three numbers there, okay? So you could imagine that as, let's just pick a point in the three-dimensional space. So in the book, this is page 256, we imagine like a cube. And you pick a point in the cube and then you read off from all three axes those three numbers, and then there you are. You've got those three numbers. Now, as before, we've got that limit up the top, the Planck limit. We would need a quantum theory of gravity to know what would happen if you had a particle that massive, and we don't. So we cut the cube off there. We can cut the cube off at zero. We know that there are particles with no mass, or light photons have no mass, as best as we can tell. Negative masses would cause really weird things to happen in the theory, things that we think are completely unphysical, and probably the theory itself is inconsistent. So there's our cube. We've got our limits, right? Don't go up here. We haven't got a theory that tells you up here. The limits are implied by the theory. The theory says don't go up here, right? If your theory is telling you that, then the number in the theory can't go up there. Zero, there's our point. And it turns out once you start wanting a universe that does interesting things, you got to sort of stay in a very specific bit of the cube. So we start cutting off bits that won't do anything interesting. And so, in particular, if you want, um, you start with the basic things and you want to build bigger things. So quarks, up and down quark. In our universe, up and down quark, protons and neutrons. They make nuclei, the middles of atoms. Throw in the electron, you've got an atom. Throw atoms together, and the electrons go around in interesting orbits. You've got molecules, and then you're on your way to making life in all those sciences that are really complicated, like biology and biochemistry and all that sort of stuff. I'll stick around this end as a physicist. It turns out if you want that sequence to happen at all, if you want the basic things in the universe to make bigger things at all, you've got to be in a very specific bit of that cube. So if
And we're still talking about mass, right?
we're just talking about masses. The reason why this matters is because you might think, oh, if I just make everything heavier, everything will get a bit heavier. The problem is at these sorts of levels, there's all these sorts of reactions that can and can't happen. I mean, life needs both. You need something to happen. You also need stability. So for the DNA is a classic example. I need that DNA strand to be able to be pulled apart so you can read out the instructions for a particular protein and then fold it back together, right? But I also need it to be the case that the bit being read off stays the same, so that my genetic code stays the same tomorrow as it was today. So life needs that sort of blend of both. Um, so with mass, because E equals mc squared, right? There's our equation for the day. Matter is a form of energy, and so when you start thinking about the processes that can and can't happen on a fundamental level inside of atoms and particles and all that sort of stuff, the mass goes into the budget sheet, right? So you draw up your budget of, okay, energy's got to be conserved in these things. So I want this process to happen. Is there enough energy for it to happen? Once you start messing with those, things start to happen that previously couldn't happen, that otherwise wouldn't happen, I should say, and things can't happen that previously could happen. So, for example, with a very small change to the constants, I can make, instead of protons and neutrons, I'll make something called a delta plus plus particle, which is just 3 up quarks stuck together. Right? So the proton was 2 ups and a down. So just stick 3 ups together. Okay? All right, there's our basic bit of the universe, right? Quarks, I made it at delta plus plus particle. What happens next? Nothing. They don't stick together. So if you can smash delta plus plus particles together all you like. The problem is this system with 2 of those stuck together, intrinsically in itself, has enough quantum wobble in it. There's enough energy there that it will break itself apart. So that breaking apart reaction is now energetically favorable. And so nothing in the universe sticks to anything else in the universe. Right? If you had a delta plus plus particle, you can put some electrons around in the orbit. You would have something that has the chemistry of helium, which is to say no chemistry at all. Helium undergoes no chemical reactions. But the short story is, for very basic reasons, once you look at this sort of 3-dimensional space and think, okay, how many of the elements of the periodic table could I actually create and would actually be stable, and how many would I actually make in the universe via any sort of astrophysical process like stars or that sort of thing? And once you've done that, you cut down to a very small sliver of this overall block with sort of complete disasters anywhere else. And so one way of breaking it up is, well, the sort of numbers involved here are 1 part in 10 to the 17 on each of those axes. So you're in a very small bit, and it's very general. Again, we're not doing anything particularly specific. It's can I take the basic stuff of the universe and make bigger things out of it? Anything bigger than like 1 particle, like a delta plus plus particle. And for a vast, for vast open areas of this of the possibilities, you can't. You just have a universe in which a whole lot of helium atoms form, equivalently helium atoms, and that's all that happens in the history of the universe.
So another example that I hear about a lot is the early conditions of the universe. So like the entropy, the distribution of mass and energy. Is that one that you like to talk about as well?
That's a
Or
that's a tricky case. I do actually give talks on that, but I sort of um, I give a whole talk on that one case. So it's a really interesting case. So here's the short story. You start thinking about a very important. When I say short story, don't get too excited. It's not going to be that short. When we start thinking about energy in the universe, there's a very important distinction between energy which is useful and energy which is useless, which is a very hand wavy way of saying, of referring to what we more generally call entropy. But you know, the rough hand wavy way is that there's energy which is in a form which is really easy to convert into another form of energy and so do something in the universe. And then there's energy in a form which won't convert into any other form and so will do nothing. It'll just sit there. So, for example, um, the air in this room is all at roughly the same temperature. And so I can't make a heat engine. I can't make any sort of engine that uses the amount of thermal energy in this bit of air right here uh, because it's surrounded by other air at the same temperature. I can't get that energy to flow in any sort of way. So I can't get it to do anything. I can't make it charge a battery or run a factory or anything like that. And as scientists thought about this, physicists thought about this for sort of a couple of hundred years, starting, probably 1700s, 1800s. There's a basic law of physics, it turns out, called the second law of thermodynamics, which in my sort of hand-wavy terminology just says you never end up with more useful energy than you started with. If you're very careful, you might end up with the same amount of useful energy, but most likely in doing anything in the universe, a useful form of energy turned into a useless form of energy, and we can always sort of analyze how that went. So this is more
that's
precise
making
than
sense.
I'm doing. There's a quantity called entropy which we know how to calculate. All right. Um, why is that the case? One of the things that was worked out by Ludwig Boltzmann, who was a famous Austrian physicist at the end of the 1900s, 1800s. I got that wrong the other day as well. Uh, Worked out was whenever you've got energy in a useful form, and you think, I can do loads with this. There's something about that arrangement of stuff which is rare. There's something, if you look at all the possibilities for how to arrange this thing, this system, if you've got useful energy, there's something rare about the way that system's arranged. This is, again, in a very precise way that we can do what's called statistical mechanics and quantify how rare it is. And entropy is basically a measure of how rare it is. So there's all those things are mixed together. If you've got a rare, special, unique-ish, not totally unique, of course, but rare within the set of possibilities, way of arrange. If you've got useful energy, you've got a rare arrangement. If you've got useless energy, you've got a very common arrangement. And so we look now at the beginning of our universe, and given the second law, it must have been the case that there was loads of useful energy at the beginning of the universe, or at least whatever the Big Bang is. Well, we can talk about that another day. Um,
Well, yeah, because you got a book out actually coming out
we
on
do.
that, right? Pretty soon.
It's more spruiking that later on, I'm sure. Um, there must have been loads of useful energy at the beginning of the universe, and Roger Penrose was one of the ones who sort of identified exactly how it is that it's useful. Is that the most useless way of arranging all that stuff is if it was completely locked away in black holes. So this is Penrose in the 70s and the 80s, and even lately he's talking about cyclic cosmologies and all that sort of stuff. So apart from that particular model of his, which is under debate, the most useless and so the most common way of arranging the stuff in the early universe was it's just all black holes, and so nothing ever happens, right? Maybe a black hole runs into another black hole, but nothing useful, nothing complicated, everything just being crushed into the center of black holes. And so there is something remarkably unique and rare about the way that our universe started, and it's just those pieces, just the second law, which is one of the most basic laws of all of physics. And this realization of Boltzmann that if you've got useful energy, you've got a rare arrangement. And you think the conclusion is that the beginning of our universe must have a very rare arrangement of stuff. It must be in a very low entropy state. This is called the past hypothesis. And so
So how rare? How rare are we talking here?
when Penrose tries to put a number on it, the number he comes up with is absurd. It's 10 to the power of 10 to the power of 123 is you got to go is 1 over that huge number gives you the fraction of the set of possibilities that you would need to hit in order to create the initial conditions of our universe. Now, that's not yet fine-tuning. That's just our universe. The question is, what does life need? And the answer is still going to be some absurdly small number, even if you want like just a solar system worth of useful energy. You're still looking at a number like 10 to the 10 to the 60, I think, something ridiculous like that. Now, those are initial conditions, so it's actually quite a tricky thing to try and think through. But I certainly, there's something there's something very interesting, very important, very special about the way our universe started, which doesn't look like just any old typical universe. In particular, every time, the way I like to say it is, every time any scientific theory has been successful, it's had to assume that the beginning of the universe is ordered. That's the implication of the second law of thermodynamics. So, that people like to say, our universe is just completely, meaningless and haphazard, and this is just any old universe thrown together. No. Anytime any scientific theory has been successful, it has had to assume an orderly beginning of the universe on very, very general grounds. Now, maybe the naturalist can just look at that and go, well, that's just the way it is. That's all there is to it. But I think at the very least, it's something that sits quite naturally if you're a theist and you think that there is actually a purpose to the universe, why we would get those special initial conditions.
Right. So I want to let you guys know, everyone watching, that we may get to your questions. I'm hoping that we can. It depends on how long we have to go here still. I want to cover a couple more examples before we move on. I actually have some objections prepared that I'm going to give him. And so once we get through those objections, then we'll see if we have time to basically take your questions. So we'll see what we can do. Well, let's do maybe a couple more examples, and let's cover. I want to talk about some that are not so well known in popular level apologetics, and maybe even just, I don't know, papers that you've seen written on it. What are some of your favorite not so popular examples of fine tuning?
Well, let me have a think. There's actually 6 quarks. So I told you about the up and the down. There's actually sort of 4 that don't turn up in ordinary matter that we see in particle accelerators. Now, again, the names are completely arbitrary. We just pick things we like. So they're known as a strange, charm, top, and bottom for no reason at all. I think
strange, charm,
top, and bottom.
Wow.
Because I mean, it's a blip on a screen. What are you going to call it? Anyway, so
I'm going to call it charm.
Charm, a charm quark.
Charm.
So, the strange quark, which again, it's a funny name, but we should move on. There's an interesting thing inside of protons. There isn't, the usual picture, which I just said was 2 up quarks and down quark, but there's so much energy in there. There's occasionally enough energy to make a pair of strange quarks. So a strange quark and an anti-strange quark for a short amount of time. So so the field is always there. They're not coming into existence out of nothing, but occasionally that field will wobble in a way that there's a charge quark, strange and an anti-strange, and then those two will annihilate back into the vacuum state of that field again.
Anti-field.
So it's kind of there at the scene of the crime for the protons, and there are some interesting suggestions that might be fine-tuned as well. If you made it too heavy, you would change the proton mass, and that can change. Again, that goes into the budget sheet of the universe as to sort of the things that you want to change. There are forces in our universe four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And there are some interesting constraints on all of them. In particular, the three that come from particle physics, the three that are there at the scene at the center of particles. Electromagnetism, if it's too strong, or too weak, you get all sorts of problems there. One of the interesting problems is stars. You want to make a star, you want to be nice and stable. Its stability is going to depend on how energy moves through the star. It's got to get from the nuclear reactions out of the star and then sort of maintain equilibrium along the way. If you get the strength of electromagnetism wrong, the way the photons, because that's their electromagnetic waves, move around, means that stars aren't actually stable. So there's some interesting stuff there. What else? One of my favorites is, and there's been some interesting work on this, is just in the earlier stages of the universe, there's basically, I call it the lumpiness. So the universe didn't start perfectly smooth. If you went out into the universe and measured how much stuff is there in this little bit of space here and how much is there in this little space there, you would get the same number to 5 decimal places. And so that's an important number. It's not 2 decimal places, it's not 10 decimal places, it's 5 decimal places. And so that tells you sort of the level of lumpiness. There's a bit more over here, so over there, but only to 1 part in 100,000. 2 parts in 100,000. No one cares. Okay. If you change that number, interesting things can happen. You could either get, if you make it way too large, you'll start to make black holes too early in the universe, and that's sort of the sort of useless energy problem we had before. If you make it too small, the universe will stay perfectly uniform, and you'll end up with the same problem as the cosmological constant. You'll just end up with protons in empty space surrounded by nothing. Nothing will form in the universe because gravity won't be able to make things collapse. So there is a sort of nice narrowish range in the middle there. So there was some constraints on this from Martin Rees, Max Tegmark, and a bunch of other cosmologists who suggested sort of maybe 1 part in 10,000 is where you've got to be. But one of the problems there is what we need to know is if I turn it up, if I make the universe lumpier, do I end up with universes which are too dense? And so in particular, galaxies that are too dense. So think about yourself on the surface of Earth, and we're going around the sun right now, okay, 29 kilometers a second, by the way. You can convert that into miles if you like. And we need all the other stars to stay away from us, right? We've got our star, which is powering us. All the other stars need to stay away. They need to sod off. There are bits of the universe where there's lots of stars flying around, and so there probably aren't planetary systems because, as a star flies past, it rips off some planets. It could be it seems to be the case that if you turn that dial up too much, you'll make galaxies in which stars ripping planets off other stars is the norm rather than the exception. Actually, there's some interesting work by a guy called Fred Adams who's doing some great physics in this area. That we're not quite sure what that upper limit is, and I'd love to know. And I'm actually sort of doing the next set of simulations where we could actually try and work out what that number is going to be, with not just back of the envelope calculations, but supercomputer simulations. So those are some of the other cases.
All right. Well, let's move on to some objections, and then we'll see if we can open it up to questions from the audience. So the first objection that I have is, well, we've only observed one universe, and so we have really no way of knowing what the real probability of a life-permitting universe is. That's objection number one.
So I think the thing that answers this objection is you just got to set up what we're doing properly in the first place. It's been said in an offhand way by atheists for an awfully long time that there's nothing special about this universe. This is just any old universe. Bertrand Russell saying that, humankind is the accidental collocation of atoms. It's all just a complete accident. And what we're trying to do is, okay, let's try and be systematic about this. Let's look at a whole lot of other ways the universe could have been and just get that whole gallery of things up there and then just look at all the possibilities and see if there is actually something that jumps out at us about this universe. Let's actually test that idea. Let's just look at the other possibilities and see whether we look like just any old accident, whether we look like everything else on the list of suspects on the board, or whether there is something interesting going on. So it's a theoretical exercise. So these other universes are other possible universes, because that's what the atheist claim was about. It was, this is just any old universe. That's saying that we're typical of all the other possibilities, right? There's nothing special about this universe. And so this is a way of systematically doing that. And the reason why the fine-tuning argument is interesting is that it looks like, when we look at these fundamental constants, there is something interesting about our universe. There would just be a whole load of, if we looked at all the suspects, a whole load of just completely dead universes in which, no two protons ever stick together. And then there's our universe where there's like a whole periodic table and people walking around and interesting stuff like that.
So sorry guys, I'm dealing with a little cold right now. That's why I'm sniffling and all this stuff. So okay, so let me just add this real quick. So Robin Collins, one of the things I like, one of the analogies he gives is continental drift theory. And so if you could say, well, we've only observed one Earth, and so we can't really say what the probability of continental drift theory is because we've only observed one Earth. It's sort of the same idea. It's kind of like a science stopper in a lot of ways. Not just science, but history as well, because we've only observed one set of historical, facts about the world. And so it looks to me like this is relying on a kind of probability, or at least strictly relying on one type of probability, frequentism. And I know that you even have a talk on YouTube about that. So did you want to add anything about that at all, or are we getting too technical here?
Oh, I mean, so yeah, you do hear this. Some people say, probabilities are, I observe one universe, and out of that one universe, one is life permitting, so the probability is 1 out of 1. And I mean, there had better be a better idea about probability than that, or science is in big trouble. Because every theory, imagine there's some data that's turned up, and that you've got like 5 theories, and you go, all right, what do you reckon? And all 5 of them go, well, look, there's one universe, and that's the data in that universe. So the probability of that data is 1 out of 1. My theory is fine. The probability is 100%. And then the next guy says the same, and then the next person says, and all 5. Like, there'd better be something else that we can say about probabilities other than I observed one thing, and so the probability is 1 out of 1. Like, if that's true, we can't use probability for anything, right? You can't. You're facing trial. Maybe this would work in a court of law, right? There's the DNA on the knife, and what's the probability that my DNA is on the knife? Well, I observed that my DNA is on the knife, and so the probability is 1 out of 1, and so well, there better be something else. Anyway, so yeah, there is a more general version of probability theory called Bayesian probability theory. It's built out of epistemic epistemic probabilities, or I particularly like degrees of support. How much does this idea support that idea? And sometimes it's 100% if it's just logical, but sometimes it's a bit less than that. I don't see any clouds out the window. How much does that support the idea that there won't be rain later today? It does support the idea, not 100%, but we can start to get a number on that. There is a better theory of probability out there.
All right, so here's a second objection. Fine-tuning has been disproven by Sean Carroll.
So I used to get this one, but people used to say Victor Stenger, and that's a great improvement to say Sean Carroll, because Victor Stenger didn't get close. He died in 2014, wrote a book called, I think it's up on my somewhere. Anyway, Fallacy of Fine-Tuning, which I wrote my review paper about. It was garbage, but that's another story for another day. Carroll's objections are interesting and worth thinking about, but I think, it depends what specific objection you're thinking of, but
so I want to make sure we're not talking about his objections to like the inference to theism. We're just talking about fine-tuning itself, like the evidence for fine-tuning, and of all the different possible universes, the ones that permit life is very small, blah, blah, blah.
So I think the main objection there from him is he said he said something like, it's possible there is no fine tuning at all, because there are cases where we thought there was fine tuning and now it turns out there isn't fine tuning.
Yeah.
Um, the case he's got a paper on this, and the case he's looking at in particular is the initial density of the universe. So, go in the early universe, how much matter was there and energy in like a square foot or something. Um, and it turns out that, a naive way of analyzing that doesn't actually line up with a way we could analyze it, which gets right into the details of general relativity. And it turns out that the number we needed, there was a good reason to expect that we'd get that number anyway. That only works for that particular number. It's a weird argument anyway. But there's sort of a triple coincidence. Here's all the possibilities. There's a special number in there from a physics point of view. Ignore what life needs. There's a special number in there. This is called flatness. Never mind the details. There's a special number in there. Life needs to be near that number. And so there's sort of a target. If you can aim for that special number from the physics, you'll get life thrown in for free. And so in this case, in other cases, it's inflation. Inflation is a dynamical process which will make the universe be that number, and then you get life for free. But so Carroll says there's also a theoretical argument why you'd expect it to be there to start with, even before you think about inflation. It's the only example of that. I mean, you look at the equations for the masses of the particles, the cosmological constant, all the other numbers. We have the equations. We can look. There's nothing special waiting for us in those equations for something to look at. So it's kind of a hope that a future theory of physics might fill in details in the way it filled in the details in the last one. But that's just sort of, possibly there exists something which is an answer to this objection. And, it's appealing to a theory that we don't have.
Yeah, like a sort of a creationist wanting to explain away evolution. Well, one day we're going to be able to explain away all the data for evolution.
Yeah. Yeah.
It's not really an objection to evolutionary theory.
Yeah, it's kind of appealing to evidence that we might get one day. In this case, appealing to a theory which we might get one day.
So are there any other objections from him that you think are worth talking about before I move on?
So there's one, and it's on my mind because I had a chat with Sean on the Unbelievable program. That was a good chat. But there was one objection there which we didn't get around to, which he raised, but I didn't answer. And it's the universe seems to be too tuned in some ways. And a good example of this we've already given. How much useful energy is there at the beginning of the universe? Well, you think life might just need a solar system worth of useful energy, but actually we've got a whole universe full of useful energy. And so things are sort of too fine-tuned. And I think the answer for that is within Bayesian probability theory, within probability theory in general, here's a bit of evidence, and we're all trying to explain this bit of evidence. And if you've got two theories and neither of them really explains the evidence at all, then it doesn't help you choose between them. And so if theism, worst case scenario, theism says, I don't know why the whole universe has useful energy rather than just the bit where we are. I have no idea why that's true. Naturalism also has no idea whether that's true if it's treating it as a fundamental property of the universe. Like the whole point of naturalism, you go, all right, that's just the way things are, deal with it, get on with it. And so if you're pulling that move, then I can pull that move as well. And so it's a complete draw. Like it's a bit of evidence which neither of us handled, and so we go on to talk about other evidence where there is a difference in the handle. So ambiguous evidence doesn't change anything, and so that's a best case scenario. That if we just have to put our hands up and say, I have no idea why the universe is like that. Well, naturalism doesn't either, so it doesn't make any difference. But there are other bits of evidence where it does make a difference.
All right, well, let's move on to next objection, which is another common one that we hear. How can the universe be fine-tuned for life when most of it can't support life? The hostility of the universe.
So again, this is simply a misunderstanding of what the word fine-tuned means. Right? I mean, it doesn't It doesn't mean a universe is not fine-tuned if it is completely full of life from start to beginning and from edge to edge. There aren't any edges for a start. There's a great I think you should just started reading it. Universes by John Leslie. It's
Yep.
still worth a read. 1989. He actually sent me an
So
email the other
good.
day. He's a
It's
great guy.
so good.
That's bang on. It's still really good. But he makes the point in there, and I wish I had the quote. But it, you can't say that the only way for a universe to be designed is if it's totally full of life, completely like packed in cheek by jowl, and everyone's just you know uh, packed in there as tight as possible. You know, it's just no part of the argument and no answer to the argument. Again, it's like before. Why is there all this empty space in the universe? And if we say I don't know, and then the naturalist has to say they don't know either. I mean, they don't have a deeper theory for that. I mean, there's no deeper reason why the universe is this way rather than some other way on naturalism. And so it's at worst a complete draw. And so it's just not relevant at all. So there is no claim being made, in particular, that our universe contains the maximum amount of life that you could get for some setting of the dials. That's just not the argument at all. The point is to compare not whether within the tiny bit of all the possibilities that allows life, whether we're the best one in that tiny little subset. The headline here is that it's a tiny subset compared to a completely dead space around it. On top of that, it's not that hard to think of reasons why there might be empty space around us. I mean, light gets through it, so we can see the rest of the universe. If you fill the whole universe with air, that might be great for a little bit, but you wouldn't be able to see more than about a few 100 kilometers into space, and 100 kilometers is not far in space. And drag forces on the Earth mean that we'll plunge into the sun within about a month. So, you've ruined a universe, right? It's just not that on theism. It's just not that hard to think of reasons why you would have a universe in which there was a specifically, there's a bit for life and there's a bit that's not for life. There's nothing in theism, particularly Christian theism, that says that we are the only reason why the universe is here. That's not any part of theism either.
So I've looked in the live chat and I can see that a few people have already started to ask questions for Luke. I'm not going to look at those yet. So I'll let you know when I'm asking for questions, and at that point I'm going to be looking at the live chat, and so I'll actually take your questions in. So don't type them in the live chat yet. I'll let you know when I'm going to do that. I have 2 more objections that I'm going to give to Luke, and then I'll ask for questions. So just hold on to your questions. If you've already asked one, just copy paste it somewhere and then give it to me in a minute. All right, so next one is, we only think life is special because we're living beings. Why aren't we discussing fine-tuning for black holes? Fine-tuning assumes that humans are the most special thing in the universe.
There isn't fine-tuning for black holes. Those are easy. You can make... So think about the useful energy. That was the most common, so the most useless form of the energy, so the most common form of the energy. Making black holes is a piece of cake because you don't need a periodic table. Any matter, any form of matter will do. So all of the constraints on you need this mass and that mass, and you've got to be in this slice, and you've got to have this force, and you go, no, that's fine. Throw it all in a black hole. That'll be great. There's no fine tuning for black holes. But more generally, the crucial bits of evidence are the ones from a Bayesian probability perspective. The really crucial bits of evidence are where you've got 2 theories, and there's a big difference between how likely the 2 theories make a given bit of evidence. So, take the example of, there's been a robbery, and there's a theory that I did it and a theory that you did it. And if we say, okay, the robbery happened in Sydney, Australia, then suddenly the probability that I did it, that's kind of, I live in Sydney. The probability that you did it from Texas, and then suddenly there's a massive difference in the probabilities there. Technically, it's a likelihood. What's the likelihood of that evidence given the theory that I did it all versus you did it? So it's precisely the case that we have 2 theories that we're interested in, and suddenly there's a bit of evidence which makes a big difference between them. So we don't assume that life is special. That's not an assumption from the start. When we look at how likely is it that there would be a universe which contains life on theism and on naturalism? Suddenly the scales tip drastically, right? It doesn't seem that unlikely on theism, given that there's a good, creator of the universe. So to create a universe in which there's, embodied creatures isn't that unlikely. I mean, stick it at 1 in a billion, who cares? That'll be fine. Whereas what fine tuning shows is if you're a naturalist and this is just any old universe, the probability of getting a life permitting one is extraordinarily small. So there's no assumption of specialness. It's just we notice as an outcome after the fact, it's a result of these considerations that these two probabilities suddenly got massively outweighed. And so this particular fact, any fact can be evidence. You don't have to justify it beforehand. The fact this universe is life permitting, that's all we need. And I'm allowed to put that into my probability calculation. And what it turns out that actually makes a massive difference. So there's no assumption at all that life is special.
All right, so I'm going to ask the last, or I'm going to give you the last objection, and then, so if you do have a question for Luke, then go ahead and write it in the live chat while he's giving his answer to this objection, and also make sure to tag at Capturing Christianity so I can make sure to get your question, and we'll go through as many as we can. I'm not going to ask all of them. We'll only get the good ones. So if you have a question for Luke, then make sure to write it down in the live chat right now, and I'll be monitoring it as I give him this last objection. So the last one is, well, how do we know that other kinds of universes with different constants and quantities and everything are even possible? So maybe the conditions that describe our universe are metaphysically necessary.
Yeah, so this is one of the objections we look at in the book. And the short story is, if you think about fine tuning and you think there's something to answer here, then that's a totally live possibility, right? Go for it. If you think you can come up with some metaphysical principle which is going to say, okay, all these other universes weren't really possible. If you think you've got a metaphysical principle which predicts the mass of the electron, for heaven's sake, let us know. Right? Go publish it it'll be the greatest metaphysical result of all time, right? People keep saying philosophy is useless, right? I mean, if metaphysics comes roaring back and predicts the mass of the electron, win, right? Every philosophy department will be lording it over their local physics department for the rest of time. If you think you've got that thing going, then go for it. So we can at least look at those ideas. And there are some out there. So, John Leslie, I don't know if you've got this bit of the book yet. He goes, his answer is he thinks that moral value is itself sort of creative in some sense. It doesn't need to be a person. Just the fact that a reality is itself morally good is enough to bring it into existence in somehow. All right, there we go. Philip Goff, I think that's his name, has a book on so he's what's called a cosmopsychism. Everything in the universe is conscious in a little way, in some way. I'm not representing that view perfectly because I don't fully understand it. But so he's been emailing me, but he thinks that would explain fine tuning because if consciousness is crucial for something to existing in the first place, then it would make sense that this basic stuff of our universe would be the stuff that if you put it together would make a more conscious agent like us. And so it must have a other set of properties. So, I mean, if you've got some metaphysical principle which is going to tell us which sort of physical universes are possible or impossible, then go for it. Let's it can't just be a hypothetical, just maybe there's something out there that could get a specific, idea and let's find out, because otherwise, there's nothing in the physics that tells us it's this way or another way. We write down an equation. There's a free parameter in it. The equation doesn't tell us what it is, and as far as principles of physics, that's it. We're done. They're all there on the piece of paper. There's nothing there, and so physics, as far as that set of equations, is done. Now, if you're thinking about some deeper set of equations, then go for it. Tell us what that is as well.
So I have about 4 questions here, and then we'll close out the interview. So the first one is from Pine Creek. Hey, Pine Creek. He says, what percentage of our universe can sustain life? If this percentage was was much higher, would you say that this universe is more or less as just as finely tuned?
Okay, again, this is not understanding what fine tuning is. Okay, this universe, well, we say this universe is fine tuned. What we really should be saying is this universe is life permitting. Okay, so think about a dartboard, and then there's the bullseye. Okay, um, we say that a perfect bullseye has to be fine tuned because the size of um, the bullseye is small compared to the overall size of the board or the wall. Okay, so this, if you then take the shot and it hits the bullseye, there's a sense in which the shot is fine tuned as well. There's a way you could say that, but when we're talking about fine tuning in this sense, it's about as I said, within the set of possibilities, the subset that permits a certain outcome is small, and so saying how much life is there in this universe is a bit like looking at some particular detail of where exactly in the bullseye the shot landed. Like if it was closer to the center versus slightly further out in the bullseye, would it be more fine tuned? Yeah, in some sense, but that's not what we're talking about. Um, in particular, it's not clear that naturalism. Again, there's a draw between theism and naturalism on that level. So that's a irrelevant fact. It's one where the probabilities don't, they just stay the same. No one cares. And so it's not in the sense of fine tuning, which is relevant to the fine tuning argument. The amount of life in this universe is not the amount of fine tuning. It's just not the appropriate thing. There's no, if there's no prediction, then who cares?
Yeah, so I think so. Reading his question back, he said, "What percentage of our universe can sustain life?" Does that change your response at all?
By volume, it's a very small number. Let's be clear about that. One more. I think I tried to work this out. I think if you do it by mass, the number is like 1 part in 10 to the 40. Like, of all the protons in the universe, one in every trillion, trillion, trillion or less ends up actually in a living thing, or
Yeah.
in some sort of living thing. On if Earth is the only one. Again, that number is not an example of fine tuning. That's just something else.
Yeah, the amount of life is not the relevant question.
And we understand why, for example, stars have to be as big as they are if they're going to give the sort of light that life needs. So even in that case, how big is the sun compared to me? The sun is 2 times 10 to the 30 kilograms. It's got 28 orders of magnitude on me at least. Does that mean? I mean, we see why it's got to be that big, why I've got to be this small in this particular setup. There's a reason for it. There's just there's nothing there that speaks of, well, this couldn't possibly be what a god would have wanted to make.
All right, so here's another question from Lewis R. He says, and this one actually seems pretty technical. He may be a cosmologist himself. I don't know, physicist maybe. It says, Dr. Barnes, there is a recent study by Colin Sarkar et al. That claims there's evidence for anisotropy. Is that how you say that? Of cosmic acceleration. That would be crucial when assessing Rice and Schmidt's work. Any thoughts?
Uh, and anisotropy. Okay, all that's saying is maybe it's accelerating that way a bit faster than that way.
Okay.
So if there's a galaxy over there at a certain speed, over there at a certain speed, tomorrow that one's slightly faster than that one. It's a standard. It's an assumption of the model that no data has ever overturned, that actually the universe is isotropic. So actually all the galaxies, it doesn't matter what direction you look.
Mm.
All of these I'm not familiar with that particular study. There've been claims about anisotropy. They tend to pop up and then go away fairly quickly. It would be a massive result. This would be crucial when assessing Reese and Schmidt's work. No, I don't think it would. You would just have anisotropic initial conditions. It wouldn't affect. Reese and Schmidt are the ones who discovered that the um, are the leaders of the teams that discovered that the expansion of the universe is accelerating. So Adam Rees and Brian Schmidt, who wrote the forward to our book, by the way. Nice. No, it wouldn't affect that. It wouldn't really affect that at all. It would probably mean that there's something about the initial conditions of the universe that would need to be different. I suppose you might suggest that there would be an anisotropic form of dark energy, but that's not necessarily true. And in any case, it doesn't actually affect the cosmological constant problem because there's still all those fields there, and they still should be producing a cosmological constant of this size, but they aren't.
Okay, so next question is from Mordic 101. He says, question for Luke, what about the more fundamental laws objection? If that would be surprising of all conceivable laws, this one, wouldn't an intelligent God also be surprising?
I'm not sure I fully. So I take the fundamental law objection as saying, okay, we don't think that the laws of nature as we know them are the last word in the laws of nature. Um, so why would we care about what the fundamental constants are in those laws? And I think the answer is to that is it's the best handle we have on answering this question of, is this just any old universe, or is there something interesting going on, or special, or rare, or remarkable going on around here? That's the best handle we have on doing it in a way that's as deep as we can go in the laws of physics and is tractable, so we can actually work out what would happen in these other universes, and we can, in various ways, get some probability estimates out of it, and we can do it systematically, look at all the possibilities rather than just all the ones we can think of. Um, I think it's not true that if you go to a more fundamental law, so we write down some deeper equation, that it will necessarily get rid of fine tuning rather than just move the fine tuning up a level. So before quarks, we would have been talking about the fine tuning of the masses of the proton and the neutron because we thought those were fundamental, and we could lay out all of the fine tuning cases for that because we know what would happen to stars if those were different. And then we discovered quarks, so there's a more fundamental theory. And all of those constraints just transferred straight up a level to the quarks, and they're all still there, and all the fine-tuning cases are made. So it's not fine-tuning's not a disagreement between theory and data. It's something weird's going on in the theory in and of itself. In this, is this any old universe kind of case? So it's not true that the advance of science will necessarily erase fine-tuning. It's just as likely that it'll make it worse. And so the fact that there could be a far more fundamental law, it's pure assumption. It's assuming the conclusion before the right at the beginning. It's pure assumption to say that that's going to get rid of fine tuning.
So what are your thoughts on him saying an intelligent God would be surprising? It would be as surprising as a sort of fundamental law or a unifying law that would explain all the fine tuning.
So I think that it seems like there's an assumption there that like an intelligent God, like you're trying to make it from scratch. Like I find this in a lot of in at least some naturalists, that the way they think about God, the way they think about God being complex is, God must be an incredibly complicated arrangement of all God's parts. What sort of God are you thinking about if you think that God sort of was a whole bunch of stuff came together and made God? That the whole point of theism is that you've got to turn your worldview upside down, right? It's actually there's an interesting discussion between Roger Penrose and William Lane Craig recently on Unbelievable, which touched on this. What's the fundamental stuff? So actually, Penrose thinks it's something like mathematics. A naturalist is going to say it's matter, and for a theist, it's mind. Mind is the most basic kind of thing out there.
Yeah.
And so saying that a mind is a complicated thing assumes that the most fundamental stuff is something like matter. And so you're not really dealing with the idea of God to start with. You're trying to crowbar a materialist God into a materialist universe, and that's not what theism is. So, no, I don't. I'm not sure if I totally get the objection. Wouldn't an intelligent God also be surprising? No, not in that sort of sense.
All right, well, let's get to the last question, and then we'll close it out. So this one is from Mickey Assume. It says, excuse me, Bayesian probability, sure, but how exactly did we calculate these probabilities, and how do they work with an infinite range? So we should probably take those separately, right? Those two questions.
So I have a paper on this, and I'm just googling to remember what the the title of the paper was. Fine tuning in the context of Bayesian theory testing, which was published in the European Journal for the Philosophy of Science. But if you just Google the title and my name, there's a preprint version on archive.org.
I should mention that you and I were actually talking about this problem years ago, and I don't know if that even sparked your paper, or you were already thinking
not
about
this
it.
one. I have another one that's actually was sparked by that. So there's a blog post on your excellent website, which is the paper isn't out yet, but there's another one which is going to deal with similar sorts of things. But you can get the simple version on, well, the less technical version on you should put a link to that.
I should.
This specific one. So the question was,
how do we calculate these probabilities?
So we're trying to get a mathematical representation of the statement. Suppose I knew that this law applied to a universe, but I didn't know any data about that universe. What would I expect the free parameter to be? Just before I even look at the data. Now, that's called a prior probability. It's a distribution in particular because it's a continuum. The important thing to say from the start is if you can't answer that question in any way, then your theory is gone. You can't calculate something called the likelihood because you have to be able to, it's called marginalization. You've got to marginalize, or getting rid of a nuisance parameter. You've got to be able to marginalize over your ignorance of that parameter if you're going to calculate what's the probability of the data given the theory. In short, if a theory can't get some sort of handle on its free parameters, then it can't do any of the stuff you want a theory to do, like predict data. And so there better be a way of us getting a handle on a statement like, I think this, what if this theory described a universe, but I didn't have any data about the universe? What would I expect this free parameter to be? And obviously it's going to be something flat and broad because there's no prior, information. And that's what you're trying to represent. It's just representing our ignorance. So this is what epistemic probabilities do. We do it in physics all the time, and we have to do it all the time. If you've got a measurement of the mass of the electron, you've got data, and you want to say something like, given this data, what's the probability that the electron has a mass in this range, say, whatever that range is? You have to fold that prior probability into it. Right? Otherwise, all you've got is just the likelihood. If you want a posterior probability, as it's called, you've got to be able to fold that in. You better have it, because if it's totally undefined, you're in trouble. How do we deal with an infinite range? Very quickly, it's there in the paper. I've sort of alluded to it already. For numbers that have dimensions, we've got the Planck limits. Right? I don't know how to do quantum gravity, so there's a limit at the top, which is provided by the theory itself, which is exactly what we want. The theories have got to control things. If you've got a number without dimensions, then you don't have to try to make the probability flat over an infinite range, which is impossible because it can't then have an area of 1. So there's possibilities about how we could do that. In the paper the next paper I've coming out, the one based on that article, I sort of go through all of these possibilities, all of these calculations for the specific set of fine-tuning parameters we have. So I don't think there's a tough problem there, but not an in principle unsolvable problem.
Yeah, and you even had a conversation with Luke. I was about to say you. You had a conversation with Tim McGrew, who is one of the original guys. Him and Vestrup, I think.
Yeah.
Is that it? Vestrup? They originally raised this problem of coarse tuning, and so yeah, it's a real big interesting question.
And Lydia,
Lydia was part of it too.
Both
okay,
McGrews, which is
twice.
Yeah, well, intimidating.
Well, they there's new. We didn't really talk about this, but fine tuning for discoverability is something that Robin Collins is working on, which sort of avoids this whole problem of normalization, is what it's called in the literature. But any thoughts on that? before we close it out?
On discoverability.
Yeah, how it kind of avoids that, and then because we didn't really talk about any fine tuning for discoverability, we were just talking about fine tuning for life. But
I think the problem is solvable anyway. So it's especially it's not a problem for discoverability or the other ones. I suppose discoverability, in particular, you can't hit it with a multiverse. It avoids the multiverse in a very interesting way. I think there's other ways of avoiding the multiverse objection, but discoverability totally wipes it off the map. If that sort of fine tuning exists, then there's no sort of fine. So my favorite example of discoverability is the universe does a whole lot of nuclear reactions in the first 3 minutes. After that, we have sort of 3/4 hydrogen, 1/4 helium. You could have had a universe which was, if you changed the dials, you could change that relationship. You don't want a pure helium universe because stars burn out too quickly. But a pure hydrogen universe would be all right. And so there's sort of a one-sided case of fine-tuning there. But for discoverability, having a quarter helium in the universe means it's quite easy to discover how much helium there is out there relatively. You're not looking for trace amounts of it. And then you've got a good bit of evidence for the Big Bang Theory. And so that's an interesting case of discoverability.
Huh, interesting. Yeah, well, this interview, we're not talking about, we weren't devoting most of it to the second part of the fine-tuning argument, which is what does fine-tuning or a life-permitting universe imply? We weren't going there. I just wanted to mainly focus on the evidence for fine-tuning, and I hope you guys got a lot out of it in that sense. So, but thanks for joining me, Luke, and maybe we can do a part 2 where we talk about the inferences that we can draw from this data.
Yeah. Hopefully that paper's out soon. So,
well, there you go. So thanks for joining me. And if you guys want to learn more about what I'm doing, head over to my website, capturingchristianity.com. And if you want to support me, patreon.com/capturingchristianity is the way to do it, and also become one of the Bereans. I don't even know how to actually pronounce that word, but it doesn't matter. Anyways, have a good night.
My new book.
Oh yeah. Talk about
Cosmic Revolutionary's Handbook. Just the evidence for the Big Bang and why we think it's a good theory, and in particular, if you want to overthrow it, here's a guide as to how you might do that.
And when is it coming out?
Coming out in February from Cambridge University Press with Geraint Lewis again.
There you go. And what I'll probably do is have both of you guys on to talk about that one. So
cool.
All right, and we'll see you guys later. So have a good one.